we're now going to use this theorem on the expected value of a sum to recompute some of the expected values we did the hard way, i.e. using the formal definition from last lecture. Okay, and we'll even do more complicated versions of that. Okay, so I'll erase this little tidbit that, this formula applies even if you have more than 2 terms in the sum, and let's now do a bunch of examples. Okay, so let's start with the sum of 4 dice. So you roll 4 dice. So 4 independent fair dice, and take the sum. So x is the sum. The measurement we take is the sum of the values. Okay, and we might ask, what's the PDF for x? So the PDF for x. So if we take the possible values of the sum, okay, and what's the probability? So the minimum sum is 4, and the maximum sum is 24. So you have 4, 5, 6, 7, and so on. And it's a uniform sample space. So 1 over 6 to the power 4, that's the number of outcomes, 1296. So there's one way to get a 4. So 1 over 1296. There's one way to get a 24, 1 over 1296. And then a 5 is 4 over 1296. And then 6 is 10 over 1296. And now you might ask, how many ways are there to roll a 7 with 10 dice, and so on and so forth. So you can compute these probabilities, and then you take the expected value of x. So the expected sum of 4 dice, you do 4 times 1 over 1296 equals 1 over 1296 times 4 plus, 4 times 1 plus 5 times 4, 4 times 1 plus 5 times 4 plus, 6 times 10 plus that. Oh, wow. Okay. So exercise. An exercise in masochism. Compute this expected value by first computing the PDF, and then computing the expected value using the formula, okay, which is the weighted sum of, you take the value, weight by the probability, and add. So exercise, compute PDF, the full PDF, and then the expected value of x, as in above. Okay, so it's a relatively straightforward exercise, although tedious. Okay, but we're going to get this expected value almost instantly by noting that if you have your 4 dice, x1, x2, x3, x4, and you let x1 to x4 indicate, the roll that each of the 4 dice got. So what was the roll on the first dice, roll on the second dice, third dice, fourth dice. So these are all random variables that can be computed on the same sample space. Okay, so when you roll 4 dice, there's a value on the first, that's a random variable. There's a value on the second, that's a random variable, and so on. And my x is equal to x1 plus x2 plus x3 plus x4. And the theorem says that the expected value of x is equal to the expected value of x1 plus the expected value of x2 plus the expected value of x3 plus the expected value of x4. Okay, and we know that the expected value of a dice roll, a single dice roll, we computed it last time, is 3.5. So this is 3.5 plus 3.5 plus 3.5, 3.5 plus 3.5, okay, which is 4 times 3.5, 4 times 3.5, which is equal to 14. Boom. So when you compute this expectation as your exercise, you should get 14. In fact, we can easily compute the expected value for n dice rolls. N dice rolls. Okay, so the expected sum for n dice rolls is just n times 3.5. Okay, now you try to compute the PDF for even the sum of 10 dice rolls, and you'll see how hard it is. But the expected value, easy to get using that theorem. That's how powerful that theorem is. Okay, now let's do some other examples. Or a binomial.